All right, so this is Cal 2, 7.5 strategies for integration. If you hear my son screaming in the background, I'm sorry about that, but that's one of the consequences from working from the house. So let's try to get a game plan for working through all different types of integrals that you might run into, because the challenge is not only using the individual techniques that we have, but knowing which tool to use at the appropriate time. So I'm going to try to give you a strategy where you're working a problem and you're not sure, what tool to use at that moment. So the first thing I would do, step one, is try to simplify the integral. So in particular, we're going to focus on the integrand, that function that we're integrating. Okay? So we can simplify this thing by algebra. Or trig identities. Okay. Example. Integral cosine theta tangent squared theta times cosecant squared theta minus 1 d theta. Okay, so when I see a bunch of trig functions, first thing I think is try to convert everything to sines and cosines. Now, if we can use an identity, great. If we can't, that's what it is. But here I see an identity. Right here, what's this identity? This is cotangent squared. Okay, cotangent squared. So I can reduce that. What about this here? Can I simplify it? Well, let's convert everything to sines and cosines and see what happens. So cosine's good. Tangent squared. Tangent is sine over cosine. So that's sine squared theta over cosine squared theta. All right. Now we talked about cotangent already, converting here to cotangent. Cotangent is cosine squared theta over sine squared theta. Now this is pretty good for us because all of a sudden the cosine squareds cancel here and the sine squares cancel here. So my integral drops out from something super complicated to just cosine. Let's see. Looks like it's just cosine theta. Okay, so cosine theta. So that's pretty slick right there for us. Integral of cosine theta d theta is sine theta plus c. Sine theta plus c. No big deal there. Okay, try another one. We did with trig identities. Now let's do one where it takes some algebra skills. Okay. So we've got a polynomial divided by a polynomial. That's a rational function. The top degree is higher than the bottom degree. Anytime that we see something like this, you should think, okay, maybe long division will help us out here. Now, if I divide this through, I get x cubed over x minus 2x squared over x plus 1 over x dx. And so this reduces to x squared minus 2, I'll take the 2 out, x plus integral 1 over x. Okay? When I integrate all these, integral x squared is x cubed. X cubed over 3 minus, let's see, looks like just x squared, and then plus natural log absolute value of x. All right, so this is going to be plus c here. How much easier was that when we algebraically simplified? So trying to do this whole thing at once, we divide and conquer. Divide it up into pieces, split up into 3 integrals, and then integrate each piece individually, and we get our answer. So always step 1, try to simplify if possible. If you can simplify it, you might turn it into something super easy, something looks really scary, and then it all just kind of drops out. So key here, make sure to convert everything to sines and cosines. Use identities if you see something that pops out. With this one, long division typically will help you out, but not always. So try this next one, step 2. Try U-substitution. I think that of all the techniques, U-substitution is probably your easiest one. So always try to go for the low-hanging fruit first. All right. So when I'm thinking about these problems, if it doesn't help me when I algebraically simplify, I think, okay, well, what's the next thing I could do? Mentally, I can look at it and say, is there a good U-sub where I see its derivative in the integrand? So let me write that out. So mentally, look for a U-sub, okay? This is why I have you guys do so many homework problems, because I want you to get to the point where you can look at it and say, okay, do I see its derivative somewhere? And it being the u that I make the function inside, okay? So if you see a function and its derivative in the integrand, then U-sub is the way to go. Okay, that's definitely the way to go. All right, so let's do an example. Integral x squared over x cubed plus 1, okay, dx. Now, I look at this and I say, okay, algebraically, now my degree of the denominator is bigger than the degree of the numerator, so long division's not really going to do us any good here. So then I think, okay, is there a U-sub that will help me out here? And if I take a derivative of the x squared, then I'm just going to get something with x, so that's not going to help me here. So I need to maybe make the denominator u. Let's see. If I make the denominator u, x cubed plus 1 is u, then du is 3x squared dx. And that's what I want, okay? I see a x squared and a dx in the numerator. So divide both sides by 3. So I get x squared dx is equal to 1/3 du. So everywhere I see that highlighted part, I'm going to replace it with this highlighted part right here. Okay, so this is 1/3 du up in the numerator. What does the denominator equal? Let me use a different color. So x cubed plus 1, that's my u right there. So let me simplify this. That's 1/3 integral 1 over u du. Now, that should be a pretty easy integral. This is just 1/3 ln absolute value u plus c. But we don't leave our answer in terms of u because we started in terms of x. Our example was in terms of x. So let's make our solution in terms of x. The indefinite integral is 1/3 ln absolute value, x cubed plus 1, close absolute value, plus c, since u was equal to x cubed plus 1. And that's your answer. No big deal. If you really wanted to get fancy, you could write ln cube root x cubed plus 1. But, you know, that's getting fancy. Okay, let's do one more of these clever U-subs, okay? So integral x square root x minus 1 dx. And I hope you're paying attention to these problems. They're really good practice for you when you're trying to figure out which technique to use. All right. So when I look at this, I'm thinking, oh my goodness, what a mess. All right, what a mess. Not really anything I can do algebraically to simplify the integrand, but maybe I can start making a U-sub. Okay, maybe I can make a U-sub. And one of the things about U-subs, sometimes you just gotta play around with it till you find a way to cancel out all the x's. So let's do that. So let's make u equal to, now sometimes I see students, they'll say u is equal to x. Well, if you make u equal to x, you're gonna end up with the same exact problem, except instead of having x's everywhere, it's gonna be u's everywhere. And that really does us no good. So this would be a bad substitution. Don't ever do something like that. So let's make u something different than x. So it's the only other real option, maybe u equal to x minus 1, okay? Then du, that's equal to dx, which, now let's see what happens here. So let's replace x minus 1 with u. So this becomes the integral. Well, I have x and then square root u, and then du is dx, so that's du. Now what's my problem? I've got x's, but I've also got u's in there. I want everything to be in terms of u. Is there a way that I can rewrite x to be in terms of u? And yes, there is. I look at this formula right here, that substitution. Can I write x in terms of u? Yeah, if I add 1 to both sides, what do I get? I get x equals u plus 1, which is exactly what I want to do. So I want to replace this with parentheses u plus 1, close it up. Now everything's in terms of u. Now you might be thinking, well, Mr. Clark, you just traded out, one bad situation for another. Well, let's try to use algebra at this point to fix it up for us. Okay, what do I mean by that? That square root of u can turn into square root u to the 1/2 right there. And what can I do? I can distribute this to each piece in here, and I get u to the, 1 and 1/2, same base, add the exponents, that's 3/2. And then plus u times u to the 1/2 times 1, that's u to the 1/2 du, okay? And once I get to this scenario here, let me move this over here so I'll have some room. So right there, technology is so great, right guys? Okay, so now all we have to do is invoke the power rule. So add 1 to it, divide by what the number is. So add 1 to it, that's 5/2, divide by 5/2. Plus add 1 to it, that's 3/2, divide by 3/2, plus c. And we can do some simplification here. Every u turns into what? Turns into x minus 1. So this is x minus 1 raised to the 5/2. Now dividing by 5/2 is the same as multiplying by 2/5. Okay. So this is equal to x minus 1 to the 3/2, and then that's 2/3, and then plus c. And that is your answer right there. Not too bad when you see the trick, okay? So Step 2, try use substitution. Okay, so sometimes your use substitution, you use it in multiple places to get rid of all the original variables. So just another trick. I'm giving you tricks, step by steps, what to try. If you can mentally skip to the right step, that'll save you time. That's kind of what we're looking for. Step 3. Try, when simplifying, in U-sub fail. Okay? Only go to this whenever simplifying in U-sub don't get us anywhere. All right? If this is the case, identify the method based off the integrand. So we're looking at the integrand, the function in the middle. Okay? So integration by parts. I like to abbreviate this IBP just because we use it a lot. This technique, you want to use this technique if one part is easy to take the derivative. Okay, so what does that mean? Easy to take the derivative. Okay, so that means something like the function disappears after you take derivatives. So like x squared, I take derivatives of this, I get 2x. I take the derivative of 2x, I get 2. I take the derivative of 2, I get 0. So after a couple of derivatives, the function disappears. That's what I'm talking about there. So it's easy to take derivatives of. And then the second part, the other part, is easy to integrate. All right, so integration by parts, you're multiplying two functions together, okay? One of them you're going to be taking the derivative of, and one of them you're going to be integrating. And you don't want to pick the one that you're going to integrate. It's something you don't know how to integrate. That's kind of silly, right? So if you see an integrand, so the f of g times, or f of x times f of, or g of x, and one's easy to take the derivative of and the other one's easy to integrate, IBP is a good guess to go from there. Now, like I've said before, it may not work, okay? But that's the step 3. Try integration by parts if it seems like one's easy to take the derivative of, one's easy to integrate. So just to refresh your memory, integral u dv is equal to uv minus integral v du. Okay, this is the formula. Remember, integral u dv equals uv minus v du, right? So let's try out an example. Okay, integral x to the 4th e to the x dx. All right, what does this look like? What's it look like? Well, this could be a lot of headache for us if we try to do it with our methods that are taught in the textbook. U equals x to the 4th, dv equals e to the x. I picked u to be x to the 4th because this one seems pretty easy to take the derivative of, and when I'm taking the derivatives, the function disappears over time. If I had picked e to the x to be my u, Yes, I can take derivatives of e to the x, but I can do that forever. And what's a derivative of e to the x? It's just e to the x. So it's never going to go away. And if I integrate x to the fourth, it's going to get more and more complicated the more integrals I do. So the reason I picked x to the fourth to be my u is because derivatives, after a while, they go away. The reason I picked e to the x to be my integration because that was what was left, but also it's easy to integrate. E to the x is just e to the x. Derivative here du is 4x cubed dx. And you can run through this method and you'll get your answer. It's just that this method takes a while to do. So this is why it's useful to use your table. Okay, the table method will take this 10-minute problem and turn it into a 1 or 2 minute problem. So remember, your table, you have a u and you have a dv. Now, the first thing I write is the integrand. I have my x to the fourth over here, that's my u, and my dv e to the x. Okay, so I take derivatives on the left side, integrals on the right side. So let's do it. I get 4x cubed, 12x squared, 24x, 24, 0. I like to just go down until I get all my derivatives knocked out. Okay, so it's my derivatives. Now I get my integrals. This one's really tough. E to the x, e to the x, e to the x, e to the x, e to the x. That's not bad at all, right? So that side's not too bad. Now, the one thing you've got to remember, and this is where it gets kind of sticky, if you don't remember this, then everything falls apart with the table. So the table says I do plus, minus, plus, minus, plus, minus. Don't forget your plus minuses. Okay, that's where, you know, the table's kind of a downfall for you. All right, so let me rewrite everything. I got integral x to the fourth e to the x dx is equal to. Now here's the beauty in the table. Okay, so I multiply across the diagonals and I integrate across the horizontals. So I'm going to go all the way down. I stopped at 0 because after 0 it's just 0 derivative forever. Okay, and then I'm going to do a different color. I'm going to do purple here for that last one just to designate. Okay, so let's do this. So I multiply, got a positive x to the fourth e to the x, and then I have a negative 4x cubed e to the x. I got a positive 12x squared e to the x, and I have a negative 12x e to the x. Then I have a positive 24 e to the x. Let me make this a little bit smaller so that I can fit it all on one line. And then my last one, I don't multiply on the horizontal, I integrate. So minus integral 0 times e to the x dx. Now the integral, this is the integral of 0. 0 times a function is 0. The integral of 0 is just a constant. So it's minus c, but we're going to say that that's like a plus c. Okay, because it's a constant. You could do plus a negative number if you wanted. So my final answer, I think I can factor an e to the x out of each one of these terms, right? So let's factor an e to the x out of those, and what do we have left? We got x to the fourth minus 4x cubed plus 12x squared minus 12x plus 24, close parentheses, and then plus c. And that's my final answer right there. So not too bad, kind of cool how that just wiggles its way out. Okay, there's one more type of integration by parts problem that could pop up, and this is the one I've talked about in class before, but I'll do it again. It's a repeater, right? So a repeater, make sure you know what you're doing when you see a repeater. Okay, So why do we call it a repeater? Well, if we try our game here, okay, it doesn't really matter which one we choose to be u and which one we choose to be dv. Because if I choose e to the x to be u, then derivative e to the x is e to the x, e to the x, e to the x forever and ever, right? And then it doesn't go away. If I choose it to be sine, well, golly, sine turns into cosine, which then turns back into negative sine, which then turns into negative cosine, which, holy smokes, turns right back into sine. So it cycles through, and I got plus minus, plus minus, plus minus, all the way through. So it's cycling through, and you get right back to where you were. So it repeats, the cycle repeats, okay? Maybe it's off by a constant, but the cycle ultimately repeats. So what you're gonna do when you have a repeater is you look and you say, okay, on the first row, I had a sine x e to the x. That's what I have for my integration. I want to look at each row and say, is it just the same as sine x e to the x or off by a constant multiple? Here for the second one, no. But here for this third one, yes, it is the same. It's the same, all right? It's the same across there. So what we're going to do is we're only going to multiply on the diagonal for a couple of them. So those two, and then whenever I get to this yellow line here, okay, that's whenever I change gears. So I change gears. Let me do a color that will probably be, all right, maybe that would be okay. Okay, that's all right. And so you can see it repeated in here. So what is this going to equal? The integral of e to the x sine x dx is equal to multiply on the diagonal, so sine x e to the x, multiply on the diagonal, negative cosine x e to the x, and then integrate on the horizontal, minus integral sine x e to the x dx. Okay, when I write this out, now I see I've got the same integral on both sides. So that's what I'm trying to solve for. So add this sine x e to the x dx to both sides. Okay, multiplication. All I've got to do is move it around. Okay, it's a commutative. A times b is b times a for multiplication. So I've got two of them now. So that's 2 integral e to the x sine x dx equals, all right, what do we have here? We got sine x e to the x minus cosine x e to the x, okay? And then all I have to do is divide both sides by 2, and voila, I have my answer. Integral e to the x sine x dx equals, well, what can I do? I think I can factor out. Yeah, let me just factor that out. E to the x over 2 multiplied by sine x minus cosine x plus c. Okay? And there you go. That's the answer right there. Okay? If you wanted to not factor it, that's cool. Doesn't, unless it really makes it look pretty, then I'm looking forward to just seeing the work and how you got to the answer. Okay? All right. Now, that's one technique, integration by parts. Another technique that we learned recently was Trig U-sub. Trig U-sub. Okay? Trig U-sub. So you see combos of sine, cosine, maybe you see secant, tangent, or it's cosecant, cotangent together. So 3 different combinations you might run into here, okay? So you see one of those, and then there's like different powers of it. So maybe it's like sine squared and cosine cubed or something like that. Okay? So with different powers. Now it doesn't necessarily have to be different, but sometimes it is. Okay. So give you an example. You see something like this. Integral sine squared x cosine cubed x dx. Okay? All right. When I look at this problem, I think, why did I take Cal 2, right? Strip off a trig function. All right, that's what we're going to do. We're gonna strip off either a sine or a cosine, and we're going to try to use a Pythagorean identity to simplify to get everything written in terms of another function. Okay, we're stripping off a sine or a cosine so that we have a differential that we can replace in a U substitution. So this is my trig U substitution. If I have odd of either one, then that's a good one to strip, because you think about the Pythagorean identity is dealing with even powers. Cosine squared x plus sine squared x equals 1. So if we can get rid of those odd, then I can solve for 1 pretty easily. Okay? So let's get rid of a cosine. Strip off a cosine, so what I mean. So I have sine squared x, and then I have cosine squared x, but then I stripped off one of my cosines. So cosine squared and cosine is cosine cubed. So it's still the same problem. It's just that now I've got my differential here. So really I'm just looking for my dy, right? So how do I do this? Okay, or my du. So how do I get this? Well, I need something when I take the derivative, it's cosine. Okay, so that means that sine would be a good candidate for u. Du is cosine x dx. How about that? Isn't that nice? So that means I need to rewrite everything over here in terms of sine. Okay, because then if I can do that, I can write it in terms of u, and I got my answer. Pretty easy. How do I do that? How do I write cosine squared in terms of sine? Well, I subtract sine squared from both sides. Okay. And this becomes what? Sine squared x, and then 1 minus sine squared x. And then what does this become? This becomes du. Right there. Du. So sine x is u, so this is equal to u squared, 1 minus u squared du. And this integral is easy peasy, because all you got to do is multiply u squared, distribute it through, and then use the power rule. Okay? So on a test, I might just ask you to get to this point here, and that shows me you knew what to do. Because if we're in Cal 2, we know how to do this. This is our bread and butter. I don't really care too much to test you over your ability to integrate polynomials. All right? Okay. So, let's try another one. Integral sine cubed x cosine squared x dx. Sounds like my son has decided to get mad again. All right, so I look at this and I say, what do I need to strip off here? Well, I see an odd power of sine. I want to get rid of sine. Okay, strip off a sine. So that gives me a sine squared x, cosine squared x, and then I put that sine x dx over to the side. So I want a differential where the derivative is sine x dx. And I run through this same game again. I make it u equal what? Cosine x. du is negative sine x dx. How do I replace? I just multiply both sides by a negative, and I got it. I got it right there. So write in terms of cosine x. And when I do that, all I got to do is use Pythagorean identity, and I can do it. Okay, if both sine and cosine are odd power, then what do? I just pick one to strip off. Strip off one of, and let's just strip off one of the sines. Okay? You can strip off a cosine, but if I strip off a sine, then when I take the derivative, I don't have to worry about the negative, kind of like here where I had to worry about the negative if I stripped off the cosine. So it really doesn't matter. You can strip off, if you're more of stripping off a cosine, go for it. But stripping off a sine is going to get you the same result. Okay, this is if they are both odd. So we handle where each of them, there's one of them that's odd. This is the scenario when they're both odd, just strip off one of the sines and go from there. You could strip off a cosine, but like I said, you strip off a sine, you don't have to worry about the negative differential. Now, the only other case would be if they were both even. Both even. Okay? If sine and cosine powers were both even powers, then we use the reduction identity. Gotta memorize this, okay? This will be on the test. You need to know these reduction identities, okay? Cosine squared x. So write it on your note card. If you don't know, you should all be making note cards. You get that little 3x5 note card. You can write whatever you want on it, front and back, okay? So if you don't know this identity, write it down on your card. Get it memorized if you don't have enough room on your card. All right. That takes care of sines and cosines. So that's one of the combinations. Another combination you could run into is like a secant tangent. So if you see like, I don't know, tangent cubed x, secant cubed x dx, okay? Both are odd powers. Maybe strip off a tangent and a secant. So secant x tangent x dx. Think about this. What's its derivative? Well, secant x tangent, that's secant x, okay? So you could let u be secant x. All right, that would be a good way to attack this. Why are we wanting to make them squared, make them even powers? Well, we think back to our trig identities. Okay, trig identities. 1 plus tangent squared x equals secant squared x. That's a Pythagorean identity right there. And so that's how those relate. I can rewrite this in terms of secant by solving minus 1 on both sides. And you got it. All right. Now, if you don't have odds, but maybe you had like evens already to start with, tangent squared x secant to the 4th x dx, they're both even. Maybe a good thing to do is to think about, okay, so secant tangent, that's a derivative, But what's another one? Secant squared x dx. That's a derivative too. So secant squared is tangent x. Okay? So tangent x might be a good one. So when you're doing these U-subs and you've got combinations of sine and cosine, U is either going to be sine or it's going to be cosine. Same with the combination between secant and tangent. U is either going to be secant or it's going to be tangent. And same with this last combination too. It's either going to be cosecant or cotangent. So you can just think about for a second, all right, if I made U equal to tangent x, because I see tangents and secants, what would that do to me? That would make it to where I have secant squared x dx. Can I move a secant squared x dx out of here and then turn it in terms of tangent? Yes, I absolutely can do that. So maybe it's best for you to just try a U-sub with one of the pieces and then see, is there a way to strip off something to get rid of that differential? Okay, so that's just trying to give you tricks there. Now, if those don't work, but you have like a secant that's odd powers, okay, try integration by parts, right? I told you about that secant cubed x dx, that nightmare of a problem. Okay, try integration by parts, and that will definitely help you out. Okay, now let's go to the third type. So we had integration by parts. We had U-sub for trig. The third technique is Trig-sub. Trig-sub. Now, Trig-sub. If you see a square root that can't be solved by U-sub, remember that's step 2 if it U-sub trick, okay? Then draw a triangle. And use it the Clark way. Pad and pen, right? Okay. So if you see a square root in your integrand, you should automatically think trig substitution. Okay, so if I have a triangle, a right triangle, ABC, what do I know? The Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared. Okay, and maybe I'm given some angle theta here. I can use trig to help me out. So here's an example. Boom. I see a square root and I see some other junk in there. I should automatically think, okay, there's going to be a triangle I can use to substitute because I see the square root. Okay, I see the square root. All right, trying to give you hints on how you can do these problems quicker. All right, so let's draw a triangle. Draw a triangle. All right, I got to think to myself, okay? I gotta think to myself. I want to use the triangle to write the integral or integrand in terms of theta. Then I want to get a function x in terms of theta. That way, I have x equals something in terms of theta. But when I take the derivative of x, I get dx equals some function in terms of theta times d theta. Okay, that's what I'm going for. Okay, that's what I'm trying to get to, so that I can make my substitution. Now I'm looking at this, all right? I'm looking at this in here, and this inside my square root is going to help me draw my triangle. Okay, so how do I do it? Well, I think about the Pythagorean theorem. Okay, I've got a minus sign in here, so I don't see a minus sign over here in my Pythagorean theorem, but if I subtract, maybe I subtract b squared from both sides, I all of a sudden have a minus sign, c squared minus b squared. Okay, but I don't want the leg squared. I want what the leg is. So how do I get that? I square root and a square root, and now I see it. So the long side, the hypotenuse, is always the positive one in here, and the leg is this negative. If you think about it, I subtract a big number minus a small number, that result will be positive. Okay, when I'm taking a square root, I don't want to deal with negatives, so it makes sense that this would be, what's going on here is I've got like 3 squared minus x squared. So what is that? So that's a leg. Okay, my leg, maybe my leg, shoot, I guess my leg would be x, so maybe this is theta. Okay, you can pick the opposite or the adjacent, it doesn't matter, it just changes, a little bit, but it will still get us the same solution. Except maybe using a different trig function, but these trig functions are related. All right, so if this is the leg, the hypotenuse is 3, and then this side right here can be found by Pythagorean theorem. I have a squared plus x squared equals 3 squared. So to get a by itself, I subtract and then square root, and that just so happens to be that substitution we're looking to do right here. So that's the third side. So here is all the information that we need. This is the important stuff. This is our triangle dictionary. Okay? So in trig substitution, it's all about the triangle. Now we try to replace each piece in here. Okay, try to replace each piece in here. Okay. So how do I substitute to get this? Okay, well, let's think about it. What trig function? SOHCAHTOA, right? Some old hippie caught another hippie tripping on acid, right? So I want adjacent over hypotenuse, that's cosine. Cosine of theta equals adjacent over hypotenuse. So that's close to this. How do I make it exactly that? Multiply both sides by 3. And so now I can replace square root with 3 cosine theta. Okay, not a bad situation. So 9 minus x squared square rooted over x dx. This, now I've got 3 cosine theta up top. Okay, what about x? Is there a way to get x? Opposite over, well, heck, we could do opposite over adjacent, but that would be a mess, right? Okay. Really, the best substitution would be to do adjacent divided by opposite, which would be cotangent, and that whole thing gets replaced with cotangent. But I don't want to get too crazy with this, okay? So x, that's sine theta, which is x over 3. So that's 3 multiplied on both sides. So x equals 3 sine theta. Okay, so I'll replace x with 3 sine theta, which gets us our cotangent that I was talking about. Now there's one thing left that we got to take care of, and that's my differential. And I want x equals something in terms of theta to get my differential dx. Okay, so now I got it. So let's do it. So dx is equal to the derivative of this. That's 3 cosine theta d theta. Boom. So you're going to be asked to find this and draw your picture in a problem. You're gonna need to do that for the exam. So replace dx with 3 cosine theta d theta. Okay. All right. So what do I end up getting? Got a bunch of 3's, but these 3's cancel. So I get 3, and I have integral cosine squared theta over sine theta d theta. Okay. Now I'm looking at this, I'm like, well, golly, I'm stuck again. Okay, I'm stuck again. Good luck, right? So I think, is there any way algebraically I can simplify? Well, the numerator degree is power 2 and the denominator is power 1. So I'm kind of thinking long divisions. But long division's kind of difficult here because I got a cat up here and I got a dog down here. Okay, those are two different things. But I can rewrite cosine squared in terms of sine using Pythagorean identity. So this becomes 1 minus sine squared theta over sine theta d theta. Okay. And then I can use my long division and break it up. I have 1 over sine theta d theta. And then minus sine squared theta over sine theta d theta. Okay. So 1 over sine, that's cosecant theta d theta. And then minus, and then sine squared and sine, those cancel, and I get minus sine theta d theta. So these are two that you have to memorize. You got to memorize them. So this is, let's think about this. I'll give you a second. See what you're thinking. Okay, think you got it? Think you got it? So, this is 3 ln absolute value cosecant theta minus cotangent theta plus c, or I'm sorry, and then minus, and then what's the integral of negative sine? That's positive cosine, right? So minus, minus is a plus cosine theta, okay? Oh wait, this actually 3 transfers to all of them. Okay, so that's going to be 3 and then plus c. Okay? All right, now what am I going to do? Because I've got thetas and I've had my original problem in terms of x. So I have to go back to my trig triangle. So go back to your trig triangle. Square root 9 minus x squared, x and 3 for theta. Okay, cosecant is 1 over sine. Sine is some old hippie, right? So instead of x over 3, it's 3 over x. So this is 3 ln absolute value, 3 over x, and then minus what? Cotangent, which is square root 9 minus x squared over x. Okay. Close absolute value. Plus 3. Now cosine is square root 9 minus x squared over 3, and then plus c. And I can do a little bit of simplifying, and I can get 3 ln, absolute value, 3 minus square root 9 minus x squared over x, plus square root 9 minus x squared plus c. Okay, if you want to pull that 3 factor out and make it an exponent of this thing in here, that's fine, but what we have written here is just dandy. Okay, that's fine. So key here is draw your triangle. I promise you, you can get away with that little trick in the book for this first part to do your substitution, okay? But even if you do get away with that, when you get your answer down here, you're gonna have to convert back. So might as well draw the triangle now instead of trying to do it later and doubling your work. Okay, we're all about efficiency here because we're going to be short on time. Now, the last of the 4 techniques that I've taught you for Calculus 2 is partial fractions. Partial fractions, best for last, right? Partial fractions going to pop up in the next couple of chapters too, so it's not going to go away. Now, use this technique if you look at it and you say, oh, the bottom can factor. If the bottom can factor, you're probably on the right track. Now, using long division is crucial. First, if when the numerator degree is greater than the denominator degree, the bottom. Okay. All right. So giving you an example, just how would we do a problem? Okay, maybe I had like 4x squared plus x squared over, or 2x, over x minus 1 squared times x plus 2 times x squared plus 2. How would I do a partial fraction decomposition here? Okay, so this is good just to practice how to separate it up. Okay, so I look and I say, okay, do I have any linear factors? Yeah, I got a couple. Okay, I've got an x minus 1, and a linear factor has a constant on top, plus an x minus 1 squared, another constant. I build up the power, build it up. Okay, so I'm good with that one. I built it up to how big it needs to be. Then I have another linear factor, x plus 2, so I have another constant. But then this last one here, this last one is no longer, this isn't a linear factor. Okay, that's not a linear factor. This is a quadratic term that's irreducible. So I need to account for any power less than quadratic. So that's a linear term or a constant. Okay, so we've got both the linear and the constant term there. And then the job becomes figure out what A, B, C, D, and E are. But sometimes, you might just be asked to set up the decomposition, and then that's all they're looking for. Okay? So you got 2 options for solving for A, B, C, D, and E. Either you pick values of x that make some of the letters disappear. Okay, so for this particular problem, if I picked like I don't know, x equal to 1, plug a 1 in, that goes away, that goes away. If I plug a negative 2 in, that thing might go away. So
x equal to 1, negative 2, those would make things go away whenever I multiply everything by this denominator here. Okay. Or multiply both sides by least common denominator and collect like terms and set each coefficient equal to find A, B, C, D, and E. Okay. So like on the left side, I'd have like 4x squared plus 2x. And on the right side, I have my A, B, C, D, X plus E kind of business going on here. And what's going to happen when I multiply through, I'm going to get all sorts of junk going in here. I've got all sorts of factors that get picked up. And so you're going to multiply all that stuff out and you'll have lots of stuff like, I don't know, I'm just making this stuff up. I haven't multiplied this out. Maybe you have x's like this. And then I look at a bunch of different things, but the coefficient in front of the term here, the x squared term, needs to match the coefficients. Maybe it's like 2a minus d x squared over here. So I would set the 4 equal to whatever's in that parentheses here, because the coefficients on one side have to match the coefficients on the other side. Okay? So like my if I had cube terms, there's no cube terms, there's no constant, so the constant would have to be 0, things like that. Okay, so that can get pretty hairy pretty fast. All right, so recap. So we've kind of covered a lot. Strategies. Number 1, simplify. If I can simplify, great. If I can't, try U-sub. Step 2, U-sub. If I can't do a U-sub, then I got to go into my Cal 2 tricks. So I either have integration by parts, set something with the one's easy to integrate, one's easy to take the derivative of. That doesn't work, and I see a bunch of combinations of sines and cosines, or combinations secant tangents, or combinations cosecant cotangents. Do Trig U-sub. Now, if that's not the case, but I see a square root, then I should think trig substitution. Draw my triangle with square roots, okay? And it's not some clever U-sub. But if I see fractions where the denominator can factor and I get linear terms, then I should think partial fractions and how can I split it up to make it work out nicely. Now, if that fails, so step 4, when all else fails, go home, right? If none of those are working in step 3, what do? You quit? No. Then try a U-sub on a part of the problem to see if it'll transform into something in step 3. Okay? So maybe I can do some clever U-sub that will turn it into a step 3, one of the Cal 2 techniques. So here's an example, something you could see in the future. E to the square root of x dx. That is a tricky one. Oh my goodness. So what could I do? What could I do? Well, let's try it. Let's try something. If I made u equal the square root of x, okay, well, taking the derivative du is 1 over 2 square root x dx. And so then I'm just stuck in there. I don't even know what I can do to get rid of the x, because I can turn this into e to the u, but dx is 1 over 2 square root x d. I'm sorry. I need to solve here. Multiply both sides by 2 square root x, 2 square root x. So dx is 2 square root x du. Well, now I got a square root x. Well, let's think about this for just a second. What did we say u was equal to? It was equal to square root of x. So this actually does go away. It becomes e to the u 2u du. Wow. Now I've got an integration by parts problem, okay? Where if I take the derivative here and I integrate here, then I'm going to get a solution rather quickly. So integration by parts, buddy. Now, if a clever u substitution gets us nowhere, this one can cause nightmares, okay? There's no u substitution here that I know of that's going to get rid of anything that's going to be helpful for us. However, I can multiply by the conjugate. Another trick, clever little ace up your sleeve, is to multiply by conjugate. So try these techniques. When all else fails, try some clever u substitution or multiply by conjugate. Always seems to pop up when you least expect it. What is the conjugate here? The conjugate is 1 plus sine x. Now if I multiply the top by 1 plus sine x, I got to multiply the bottom just to keep it the same. Okay, I'm multiplying by a clever 1. That's all math really is figuring out how to multiply by 1 and add 0. That's all there is to it. So when I multiply this and this together, in the denominator, I'm going to get 1 minus sine squared x, which is pretty cool for us. Why is this a good thing? Why does this help? Because this is really just cosine squared x in the denominator. And now I can use long division to simplify. Get 1 over cosine squared x plus sine x over cosine squared x. Okay? So this becomes integral secant squared x. Reciprocal of cosine is secant. And then this becomes, well, I can rewrite this as sine x over cosine x times 1 over cosine x. Sine over cosine is tangent. And 1 over cosine, that's secant. Secant tangent x. Ooh, that sounds like something that we should know. So the integral of secant squared is tangent. The integral of secant tangent, tangent secant. This is secant x plus c. Now we took a problem that was pretty challenging and we converted it pretty quickly. Okay. That ends 7.5. Okay. So all the different techniques and then a strategy to work through it. Because these problems on your test, they are not going to be in order. And I'm not going to tell you, hey, use integration by parts here. So it's your job to be able to look at it and say, Okay, can I reduce this before I start it? No. Okay, is there a u-sub that I can do if I take a derivative? I see the answer in there in the integral? No. All right, then I got to jump to step 3 and then run through all my Cal 2 tricks. And if that doesn't work, try a u-sub that will convert it to a Cal 2 trick or multiplying by the conjugate. Right? And if all else fails, go watch Netflix. All right, guys, good luck.